Okay, so welcome back friends, welcome back in another video tutorial from microbiology with Shagni. So in that video tutorial we are going to discuss about a new kind of electrophoresis technique that we have not discussed earlier, that is isotachophoresis. Okay, so isotachophoresis, if we zoom it and try to decode its name, so isotachophoresis means iso means same. Okay, as I have written here, tacho means speed and phoresis means travels. That means isotachophoresis by its name want to say us that I provide separation at the same speed, right? That means the samples to be separated with the help of me are migrating at the same speed, right? So it is based on a principle that we are not going to discuss about today. We will discuss it about some other videos, that is the moving boundary electrophoresis concept. Okay, and on the basis of this our isotachophoresis works. Now all the ions being separated are moving here at the same speed as its name suggests, right? Now, so remember isotachophoresis, in isotachophoresis sample ions are separated in such a way that all the ions are stacked in discrete zone. Okay, so separation is on the basis of their electrophoretic mobility. So what is the term electrophoretic mobility suggest? So electrophoretic mobility simply wants to tell us about the migration of an electrical ion or any kind of ion under the influence of a electrical field. Okay, so it can be defined as a ratio of migration rate of an ion to the electrical field, that means V by E. Okay, and it is denoted as mu. So the migration of an ion in an electrical field is referred to as electrophoretic mobility, and on the basis of electrophoretic mobility isotachophoresis separates molecules in such a way that they are stacked in discrete zone, right? So let's see how. So I am going to use this drawing to explain you what is going on in case of isotachophoresis. So here we are using a discontinuous electrophoretic system. Okay, so in discontinuous electrophoresis system we are using two kind of, sorry for that, here we are using a discontinuous electrolyte system. Okay, because here we are using two kind of electrolyte, that is Le and Te. So Le means leading electrolyte and Te means trailing electrolyte, and our sample is added in the interface of leading electrolyte and trailing electrolyte. And I also want to describe you that leading electrolyte have higher mobility. Okay, and Te, that is trailing electrolyte, has lower mobility, and in between them the intermediate that is our sample have intermediate mobility. That means when after attaching appropriate electrode at appropriate direction we switch on, there will be a electrical field generated, and under the influence of that electrical field the leading electrolyte will first migrate towards its electrode. Okay, and it will be followed by our sample, and in the sample the mixture will be migrated at the same speed depending on their electrophoretic mobility. Okay, that means X, Y and Z here all are moving at the same speed. Okay, but depending on their differences in electrophoretic mobility, if we consider that Y has highest electrophoretic mobility, then Z and then X, then after some time we will end up with Y just following the Le, then Z will follow the Y and then X. Okay, so that is how electrophoretic mobility will separate molecules or will separate molecule in discrete zones on the basis of their differences in electrophoretic mobility. Okay, and after that the trailing electrolyte will follow the sample ions. So that's how the a separation technique is going on in case of our isotachophoresis. So the entire rearrangement depending on the differences in electrophoretic mobility will going on up to a certain time, and after that there will be a period in which we will end up with a equilibrium. Okay, and under that equilibrium the sample will be kept moving at the same speed depending on their electrophoretic mobility. That means after certain time we will end up with Le, then Y, then Z, X, and at the last Te. So that is how then our sample will be kept moving until or unless we are switch offing the current. Okay, so that is how the separation is going on, and as you can see, as a result of separation, all the ions or all the sample are stacked into discrete zone that can be easily distinguishable, right? So that is how, on the basis of their differences in electrophoretic mobility, we are separating samples. So as I have written here that after some time equilibrium will be established, so at this point all the ions will move with the same speed in discrete zone depending on the order of their mobilities. Okay, so here the differences in electrophoretic mobility will play a great role. Okay, and that is nothing but a change or in a ratio of their migration rate to the electrical field. So here we are now, let's take a situation when in your sample mixture you have two samples that have relatively very close electrophoretic mobility. So what can you do under such circumstances? Because normal isotachophoresis will not going to solve your problem because they have too much closeness, right? Suppose in a football match, after 90 minutes the score is 0-0. So what we have to do, we have to break the tiebreaker. So we will play extra time, and after that extra time we will move on to tiebreaker to distinguish the winner, right? So simply in case of our isotachophoresis, if suppose the X sample ion that we are using have a minor difference with its electrophoretic mobility of Y, then not only isotachophoresis will not go to going to solve our problem. Okay, so we need something more. So here we are using a synthetic ampollite called spacer ion. Okay, so this spacer ion, remember, have intermediate electrophoretic mobility between your sample ion that are having same electrophoretic mobility, near about same electrophoretic mobility. Suppose if it is 7, if it is 8, then your spacer ion will have 7.5. Okay, so but in such a way, by using spacer ion, that is synthetic ampollite, you can separate the sample who have very minor differences in your electrophoretic mobility. Okay, so here the spacer ion we are using is exactly the spacer ion we are going to use, or we have discussed also earlier, that in isoelectric focusing. Okay, so spacer ion will simply sit at the in between the X and Y and separate X and Y, right? So that is the idea of spacer ion. So what is the utility of spacer ion in isotachophoresis? That is the idea, that spacer ion will separate molecules having a similar electrophoretic mobility. Okay, so now application: separation of the charged substances can be done, very useful in industries for pollution control, used as a quality control, and very small amount of sample can be separated. Okay, so as you can see that we are using spacer ion for separating small amount of sample, used as a quality control method, used as a pollution control method, and separate charged substances. Okay, so that is the concept of isoelectric focusing. Sorry, not isoelectric focusing. So that is the concept of the isotachophoresis, right? So isotachophoresis is based on the moving boundary electrophoresis. Here, as its name suggests, here all the ions are migrating at the same speed, and here the sample mixture are separated in such a way that they are, suppose XYZ, they are separated in such a way that they are stacked at discrete zone. And remember, here the sample ions are separated strictly on the basis of their electrophoretic mobility, that is V by E. Okay, that is the migration rate of an ion in the electrical field in which it is migrating. So here we are using a discontinuous electrolyte system that contains a leading electrolyte, a trailing electrolyte, and in between the leading and trailing electrolyte we are adding our sample. Okay, now leading electrolyte will have higher mobility and trailing electrolyte will have lower mobility, and in between them the intermediate mobility will be for samples. Okay, now when we will switch on the heavier our higher leading electrolyte will migrate towards its preferable electrode, then our intermediate electrolyte will move, and in between the intermediate electrolyte the sample will move on the basis of their differences, in electrophoretic mobility, right? So suppose y, if y have higher intermediate electrophoretic mobility in between x, y, z, then y will follow the leading electrolyte. Then if x have higher electrophoretic mobility in between x, z, then x will follow the y, and at last z, and then te. That is how the separation will go on up to certain time. After that there will be a equilibrium point in which, or after which, there will be no rearrangement, right? That means they will move at the same speed in a same arrangement, right? And in which all the ions are separated in discrete zone, and they are stacked in those discrete zones also, right? So that is how you can separate molecules on the basis of isoelectric focusing. Sorry for that again. That is how we are separating molecules on the basis of isotachophoresis, on the basis of electrophoretic mobility, right? And now if your two of your sample have very similar electrophoretic mobility, then under such circumstance, remember it very carefully, you can use a synthetic ampollite called spacer ion. Okay, this spacer ion have intermediate electrophoretic mobility between two sample ion of the mixture. Okay, so as a result, spacer ion will sit in between y and z and separate the two molecule for you. Okay, so that is the concept of isotachophoresis, which you can use to in industries for pollution control, for quality control. You can also use the concept of isotachophoresis to separate charged substances, and very small amount of the sample can be separated with the help of this method. Okay, so I hope this video will be helpful to you, and thank you for listening to this class.